All right, hello, welcome to the Off by One security stream, our first one in October. Sorry about not having a couple streams. I had a private stream last Saturday for YouTube members on software cracking, and it's one that we can't show and put up on YouTube, or else the channel will be demonetized, taken down, whatever, because they'll consider that to be actual hacking. And I just really didn't want to go through one of those crack me challenges, because the crack me challenges aren't as real world as doing it in a real way. So I'm going to post a video of that to the members channel. So anybody who does become a member will be able to see that. But that's what I was doing last Saturday. I was also working on getting some additional upcoming sessions. You may have seen, I tweeted it out. We've got, of course, NOP today. And then we've got upcoming, we've got Chompy. We've got Jim Shoemaker to go through multi-factor authentication. Chompy just released a paper, like a blog, about her research and how she goes about things. So that's going to be more of her kind of walking us through her methodology, less of demonstration and more of her talking and answering questions, which will be a great opportunity. Got a few other streams booked and in the works right now as well. Some really cool stuff. And I'll just continue to post that so you know what's coming up in the next month or so. Oh, and I just added another one. It's going to be on offensive AI. So I've got this individual, Foster Nethercott, who's going to come on. He's authoring a new course on offensive and adversarial AI, and he's going to come on and walk us through some cool things that he's uncovered during his research. So I think that's obviously a fascinating area that's very contemporary, and people want to know more about it. But this week we've got Nop. You want to say hi?
Yeah, hi. Thanks for having me on the stream. And yeah, just like in Amsterdam, I'm looking forward to talk about CFG and my favorite CPU register again.
Yeah, for those of you who maybe missed it, we had a hack fest in Amsterdam a couple months ago, and Nop came out and spoke, and it was a really great session. So I thought it would be a good one to bring to the stream, and here he'll have more time and won't be under that pressure of, you got to be done in 35 minutes or whatever you had. Control Flow Guard, of course, if you're not familiar, is other operating systems have leveraged it as well in their own way, but Windows was the first, I think, to come out with it in this vein, in this style anyway. And I remember back a number of years ago when the Enhanced Mitigation Experience Toolkit, EMIT, from Microsoft was a suite of mitigations that were not turned on by default. You had to download this toolkit, and then it primarily focused on user mode mitigations. And if you turned it on, I remember Microsoft did this a blog, and they basically said they ran somewhere around 100 exploits that were all patched, but they took an unpatched Windows box. It was Windows 7 at the time, and they ran 100 what would be 0 days against them because it was unpatched, right? And they were able to get in with most of them. And then when they turned on EMIT with all the different mitigations enabled, it blocked somewhere around 90% of them. And their point was that this blocks 0 days because it focuses on the techniques that attackers use to execute the payload. In a prior stream, I walked through looking at the mitigation EAF plus, which was the, what's that stand for again? Export Address Table Filtering. And that's a mitigation targeting shellcode and the way that shellcode tries to resolve functions within the exports tables of like kernel 32. And we looked at exactly how that worked, and it was a fun one. And that's one of the many mitigations that come with these toolkits. And then Microsoft said at the time that there was around a 5% or less than 5% adoption rate of that toolkit, meaning that most organizations, most people were not using it and leveraging it. They finally announced it would go end of life, and that was a few years ago now. And at first, people were upset about it because the people who did use that were sad to see it go, because there were a bunch of different mitigation bypasses. And even, I remember FireEye, I think it was, discovered a vulnerability where if you got code execution, you could replay the DLL entry code with a different flag argument, and it would basically unhook all the mitigations. So the emit.dll library was still loaded into the process, but it wasn't able to do anything. It just had to watch. And so since they ran at end of life, theoretically, the mitigations would still work. But if someone finds a bypass at that point going forward, then it would no longer be useful. And their response or justification for not continuing to support it was, one, the low adoption rate. And then they also said, getting to my point, control flow guard was going to like fix all our problems. And that's what Nop's going to be talking about today. And if you know from a high level how control flow guard works, you know, nothing's perfect. There are always potentially ways to get around things, whether it be you're going after the JIT compiler or trying to find, and Nop will explain it, the way the bitmap works and the address alignments, where if there's a function entry point within this region, you can jump in there. So you can still leverage gadgets or whatever you're looking for. But again, Nop will get more into that soon. But the point is that it was clear that that mitigation was not going to solve all of our problems. And so thankfully, in the fall creators update of Windows 10, few years ago, they introduced something called exploit guard. And exploit guard kind of brings back all those mitigations, or most of them, that were there with the Emmet toolkit, and also some additional mitigations. So the enforcement of mitigations like shadow stacks and control flow enforcement technology, like those are all part of Windows Defender exploit guard. But specifically, CFG is definitely one of those mitigations that a lot of people struggle with. And it works in an interesting manner. So it's great to have Nop here to explain it to us. I remember also seeing Tavis Ormandy one time tweeted, I had to spend all weekend bypassing control flow guard to get my exploit to work. And of course, he got it working. It's Tavis, but it just shows you again that you can get around it. And one last comment I'll make is there's a tool called Ropper. I'll post a link up to it soon. It's from a guy named Sasha Shira. And somebody, a contributor to that tool, set up an option for control flow guard bypass. Basically, it will help you identify ROP gadgets or whatever it is that might allow you to bypass control flow guard. So again, just saying that no one mitigation is going to solve all of our problems. With that being said, go ahead, and if you have questions, please do post them up and ask. And obviously, just like when we had Alyssa Assange on a couple of weeks ago, if he's in the middle of a thought or trying to explain something, I don't want to interrupt him. But if it's a good opportunity to ask a question, I'll do that. Worst case, we wait till the end and we'll get back to those questions. You may have to repost it, but we're not ignoring you or anything. Just a quick big shout out to members. Really do appreciate anyone who subscribes as well as joins as a member, because that supports the channel and allows us to give back to the community. And we've got some cool things coming up with giving back to the community. One thing, I'll bring this up a little bit later on as well, is we have some scholarship ticket opportunities that we reserved for people living local in the Los Angeles area, especially students, but you don't have to be a student to get into Hackfest for free. It's a complimentary ticket. It's $425 otherwise. It's a limited number. I've already got a few takers on it. But if you are in the LA area and you can 100% make it, it's October 28th and 29th in LA. In Hollywood, we've got Yarden Shafir, who's been on the channel before, as well as David Weston, from the head of OS security at Microsoft. He's going to be doing the day one keynote. There's about 16 talks, a bunch of workshops on AI hacking and things like that, offensive AI. And we have a big night out planned for day one. We're getting a tour of Universal Studios backlot. We'll all be going on like a private tram. Get to go back and see where films are shot. Get to go on some sound stages. And then afterward, we'll go over to a restaurant and get food and drinks. But I'll bring that up a little bit later on if time permitting. But do reach out to me on Discord or on Twitter if you're interested in that. And without further ado, I'll just ask Nop, why don't you go ahead and give a little bit of background to folks about yourself, and then we'll jump in.
Yeah, sure. So I'm Niels. A lot of people might know me as Nop from online. I was pretty active in the offensive security, OffSec community. I'm currently a graduate student, so writing my master thesis right now, and I'm a red teamer at Mentodea Security in Germany. And at my day job, I'm also doing a bit of research for memory corruption, exploit development related things. And actually 1.5, 2 years ago, after I did this OSED course from OffSec, I wanted to step it up a bit and wrote my first thesis about the Windows control flow guard. So the thing we are going to talk about today. And yeah, you kind of already took away my conclusion that no mitigation is perfect. So yeah, CFG is definitely not the solution to everything. And we will talk about what it can do and what it can't do in the next couple slides, and I prepared 2 demos as well. So yeah, and I'm also kind of trying to monitor the chat as well. So otherwise, I'll just rely on you, Steve, to kind of forward the questions. And yeah, please, if there are any, feel free to ask whatever related to CFG.
Yeah, totally. And absolutely repeat what you said that I stole already at the end, because there's going to be a lot more people on by that time and they won't have heard it. So please do repeat that.
I will.
All right. So, and you found a couple CVEs not too long ago too, right?
It's the one I'm presenting is, well, it's actually just one in the like endpoint manager software from Ivanti. So yet again, the same company. The other CVE we are taking a look at is from, I think, Google Project Zero discovered it initially. It was this type confusion in the Chakra Core JavaScript engine that led to an arbitrary read-write primitive. And I actually used that CVE to showcase the limitations of CFG in my thesis. Shout out to Connor McGarr, who assisted me with writing the POCs, even though every time I tell him, I'm going to talk about CFG and I'm going to mention your name because you helped me with the POCs, he's like, it's okay. No need to do that. But yeah, just standing on the shoulder of giants, we are taking a look at one CVE I found and the other one to kind of highlight yet again what CFG cannot mitigate, because there are a lot of misconceptions about this exploit mitigation somehow.
Yeah, it's definitely one of the more just mysterious ones out there. So I'll go ahead and let's share your slide deck and I'll let you go through. I know you got a lot to cover.
Yeah, so yet again, Windows Control Flow Guard, what it can do and what it can't do. So first of all, what is CFG? As we already mentioned like a couple times, it stands for Control Flow Guard. And it is based on like CFI, so Control Flow Integrity. What it's trying to do, contrary to, for example, ASLR or data execution prevention, it tries to actually protect the control flow of the application. Now it's forward edge. We will come back to what exactly this means in a bit. And what it does, it tries to mitigate vulnerabilities that rely on function pointer overrides. So for example, use of the free vulnerabilities that we had with browsers, especially back in the day with Internet Explorer. And on a very simple level, you have your legitimate control flow of an application. So let's imagine you have a Hello World program that just prints that string 3 times. Basically, what the application does is it goes from top to bottom and executes all the code. So this is like the legitimate or the intended control flow of the application. And this is also what CFG is trying to protect, but only forward edge. So when we have an indirect function call, we have that with like object-oriented programming. We have an object, for example, the classic university example, you have your class dog and the dog can bark or run or eat, etc. Those functions of the dog are being called indirectly. And what CFG does is during this I call or indirect function call, it validates that the target address you want to call is actually valid. Now, what we do with like use of the free vulnerabilities is we attempt to hijack the VF table, the virtual function table that stores all the addresses of the object. And now if we somehow hijack the, for example, bark function of the dog, and then for some reason the program is later on calling that function, even though, for example, the object has already been freed, or we were able to somehow corrupt and override the VF table anyway, it actually then calls the value we placed there. So for example, the stack pivoting gadget address that moves the control flow to like the ROP chain if we have to bypass DApp as well, or to the shellcode if there is no DApp in the first place. So CFG is trying to only solve this problem. A lot of people that I talk to think that it also kind of kills or tries to mitigate the vanilla stack-based buffer overflow kind of thing, like the return address one, where you overwrite the return address in order to gain control over the instruction pointer and then move to your ROP chain. Though this is what forward edge means, CFG does not protect from that. So to kind of take that away already, if you override the return address on the stack, that's basically a CFG bypass already. And what we have for that scenario is, you mentioned it before already, is CET, the control flow enforcement technology from Intel, that tries to protect the return addresses on the stack using the so-called shadow stack. A quick side note, because I also wrote an academic paper about CFG, and the peer reviewers of academic papers always like performance. So the performance impact of CFG is very minimal. We tested it with chakra core and used JavaScript input files that either relied very heavily on virtual function calls or not at all. And the performance impact is very important to exploit mitigations, because Microsoft, back in like a couple of years ago, they tried to implement a software-based alternative to CET called the return flow guard. But if you take a look at the exploit settings of Windows, you will notice that it's not there. And that's because RFG was never actually shipped with stable versions of Windows, because the performance impact is too big. So if you want to develop and implement a new exploit mitigation or stack protection or whatsoever, it is very important that you keep the performance impact as minimal as possible, because the example I like is if you play your favorite video game at 100 frames per second, and then Microsoft decides to ship this new exploit mitigation, which kills all the bug clauses, but it also reduces your FPS to 20. As a gamer, you will just navigate to exploit settings, look for this new mechanism, and disable it. So if the performance impact is too big, or also if software is not compatible with it, in the end, a majority of the end users will just disable it again. So luckily, we will take a look at the actual function, the routine of CFG later on. It is very minimal, and hence nowadays it is also on by default on Windows 10 and Windows 11. So what I did for my thesis was reversing CFG. And first of all, we should understand how an indirect function call works. So if we take a look at this assembly code, it is not that complex. What we do in the first line is just move the address of the VF table into the rex register, then dereference it. Line 3 is not important right now. And in line 4, we call the dereferenced RAX, which is, by the way, my favorite CPU register again. So this call is actually how an indirect function call works. If we were to call the first function in the VF table, if we were to call the second one, for example, we would just add the offset size of the memory address. So, for example, for 32-bit, it'll be EAX plus 4, or for 64-bit, it'll be RAX plus 8. And if we are able to override what RAX points to, we can essentially just hijack the control flow of the application. Now, this is what it looks like if you compile your application without CFG. So this is how it used to look like for a very long time, until CFG actually was implemented by Microsoft. And if I remember correctly, Microsoft started working on it or like proposed the idea internally in 2012. And it got shipped with Windows 8.1, if I'm not mistaken. So you can see it takes a long time to actually develop the security mechanism, the exploit mitigation, then test it, then you ship it, and then it takes another quite long time to set it to enabled by default. Now, if you were nowadays to compile your application with CFG, it would look like this. We once again get the address of the BF table, dereference it, and this time we also save the target address, which is now moved into RAX in line 3 on the stack. And instead of just calling the target address, like call RAX like before, we will now call the guard dispatch icall function pointer. And this function pointer simply points to ntdll ldrp dispatch user call target, which is the like validation function of CFG that determines whether the target address is valid or legitimate. In that case, you can actually call the function and everything goes on. If it determines that the address you're trying to call is not valid, it will just terminate the process, just like with, for example, stack cookies. If you have a return address override buffer overflow thing and you override the stack cookie as well on the stack, it will just terminate the process. So this is pretty much the same concept, and we will see that later on in the demo. Here again, this is from the Windows Internals book, part 1, 7th edition. It showcased just how the CFG works. So you save the target address, call the function, and that function just determines, okay, is it valid or not using the CFG bitmap. And the CFG bitmap showcases why performance is very important, because in the very beginning, at least to what I heard from Microsoft employees, is they, for like 5 minutes, probably, they thought about using just like an array, a list, to determine which address is valid and which is not. But if the very last entry in the list is the one you're looking for, the runtime for that the function is just way too long, and it would also take too much memory in your system. So what they did instead was use a bitmap that allows an address to have 4 states using 2 bits. So either the address is valid, in that case you can make the call, the execution continues, everything is fine. The address is valid but suppressed. So a developer or also Microsoft can determine that a certain function, like for example virtual alloc, which is often used to bypass DEP, is suppressed and hence cannot be called indirectly. If CFG kicks in and sees you're trying to call virtual alloc indirectly, it notices that yes, you're actually trying to call like the start of a function, so that should be fine, but it's on a blacklist, so we will still terminate the process. And the other edge case is usually when you compile your software, the compiler makes sure or tries that your functions are 16 bytes aligned, but due to special compiler settings or optimization or also JIT, this might not always be the case. So if it sees that the address is not where it should start, but it's within like a 16-byte boundary range, it is also determined valid and the execution continues, which actually was not part of the initial version of CFG. So you can see that during the process of implementing CFG, Microsoft also updated it throughout the years and implemented support for those edge cases. If you take a look at the function I mentioned before, the LDRP dispatch user call target, you can see that it's very small. Now, how I like to describe it is that it does a bit of like bitwise operations magic. And we will, yeah, if time allows, we will take a closer look at this later on. I'm not the best when it comes to like bitwise operations and explaining and understanding them, but this is kept very straightforward in order to reduce the execution time it requires. And you can see the two highlighted blocks in green are just jump RAX. So that would be the equivalent of the call dereferenced RAX from before without CFG. So the very left should be the case of, yes, it's a valid function or a valid address. We can jump to it. The one in the middle is the edge case scenario where it's address that is 16 within like the 16-byte boundary range. And on the right, we can see the other case if the address is determined invalid or if it's on the so-called blacklist. It will call LDRP handle invalid user call target, which in the end will just terminate the process. So the next thing we are going to take a look at, this time actually live. Unfortunately, in Amsterdam at the Pentest Hackfest, it was not possible to present live demos. So this time we shall pray to the demo gods and hope that everything works all right with the CVE. I discovered that in May or so, or at least it got published in May. At my workshop, a day job, I researched the endpoint manager agent from Ivanti and determined or found out that the way they handle packets was not the best. And also, we are talking about enterprise software. So as a little side note, ASLR was not a thing there. So yeah, instead of going through the slides like I did in Amsterdam, I will just showcase it live.
Did you make an offer before this just to make sure they appease the demo guys?
Always. I don't want to upgrade it right now. Let's see. Where is the IDA database? There we go. So, oops. What we have here is, that was the wrong key, is the function where I started reversing it. So the function basically, I hope it's large enough, the font size, otherwise I can probably make it a bit bigger.
Yeah, if there's specific code blocks you want folks to see, definitely try to zoom in a little bit because sometimes it can be kind of small.
Let's try 14
That's perfect.
then.
Perfect.
All right. So just a quick of back information, side information to this application, to the degree that I understood it, because I've never worked with that binary in the intended way. All I did was take it apart and break it. What we have is like a call to the connection receiver function. Great.
Something locking up. Is it me or did he freeze? Yeah, you guys can still hear me, right? Just to make sure, I want to make sure it's not me that's having bad internet connection or something. Just watching the comments. Comments take, Yeah. Okay. Great. Yeah. That's a pretty early. The demo guides usually give you a few minutes before they go in and do this. They don't usually get you right at the beginning. So hopefully he'll be back on soon, and and we'll be able to move forward on this. Yeah, let's just give him a moment here. Yeah, I saw that one comment though while we're waiting for Nop to come back. Whoa! All of a sudden, I'm huge. Saw that one. Yeah, he told me that before we started the stream Legacy. He was like, my computer might freeze and I'll have to come back on. So hopefully I'll only have to do that one time. But I saw the question about counterfeit object-oriented programming. That's a neat one. One of the mitigations that's come out, obviously, and thankfully it's not on in most situations yet because the processors haven't caught up, but it's shadow stacks. And the way shadow stacks work, if you're unfamiliar, is that normally during a call instruction, the next virtual memory address where the program counter would be pointing, let's leave speculative execution out of this, but the next address that the program counter will be pointing to during the call instruction gets pushed onto the stack, right? And we normally just overflow it, and then we can redirect the flow of execution when we hit the return instruction. The shadow stack is a newer mitigation where it pushes a second copy of the return address onto the shadow stack that's supposed to be hardware protected. And the only instruction that should be permitted to be able to even push something onto the shadow stack is the call instruction. And so if you go to return and it's desynchronized, where the active stack that you've overwritten does not match the address as what the return pointer should be for the shadow stack, then it will terminate. It's not going to let you continue. So it's a pretty nasty mitigation between shadow stacks and then control flow enforcement. The way that the basic control flow enforcement technology works is that normally when we return back from to a caller, whatever that next instruction is supposed to be, it's supposed to be. But what it does is it puts a new instruction on that's called N branch 32 or N branch 64. And it's basically a benign opcode. It doesn't do anything, but the rule is that it has to be there. So every time you return back from a function call, then you have to execute the N branch instruction. And as you can imagine, if you're doing return-oriented programming, you're not going to be able to find ROP gadgets that are really usable because every ROP gadget that you return to has to be an N branch instruction. So when you combine that control flow enforcement along with shadow stacks that I just explained, it really does kill buffer overflows on the stack and really does kill return-oriented programming. So people, of course, been trying to come up with additional ways. One was the counterfeit object-oriented programming, which is specifically going after shadow stacks and the limitations there. All right, I was just covering time for you while the demo guides got you right at the beginning. I can't hear you, by the way. I can see you, but can't hear you. Still can't hear you.
Still not?
Yep, now I can hear you.
Okay.
Perfect. All right,
Weird.
continue.
Weird. Yeah, so people who know me should be familiar with that problem. On Windows, it's even worse. But yeah, my PC has a habit of just breaking. It's probably mad at me for something. And hopefully this is not going to happen again today. But yeah, the last Linux update was probably not the best one. So back to it, and hopefully I can explain it without any crashes this time. What we have for this Ivanti endpoint manager is simply this binary listens on your PC for incoming network packets to probably somehow allow some degree of remote management of an employee's PC. And I already mentioned it before, they did not implement handling packets the best way. So what we have is just the call to connection receiver that sets everything up and uses the receive function to actually receive data from the probably management server. Now we have two calls to it, as you can see here. And let me make that bigger again. So we have the first call to connection receiver, which kind of like receives the network, the packet header. And depending on the data you send there, it uses that amount. So you were able to specify like a length or size field, and it uses that amount, which is stored in EAX here, to receive that amount of bytes in the second call. So we can see that it checks for hex 7 FFC, and this is the upper limit of bytes you can send or that the application can receive in the second call to the receive function. So if we go here, we are just kind of stepping through the application. This function does a bunch of checks on a heap object that was unrelated. And in the options menu, you were basically able to set an opcode in the packet. And depending on that opcode, different functionalities were triggered. Now you can already see that if we hit this basic block, we call the function IAMVuln. And what Ivanti did in this function was great. Let's see if Ida's coming back. But anyway, what Ivanti did in this function is they used the string copy operation to copy data onto or into the .data segment from the packet body you send to the application. Now, copying data into the data segment by itself, or at least writing outside the allocated buffer, I don't know if Ida can actually showcase that. So we have an destination char array of 260. But if you remember from earlier, we were able to send up to hex 7 FFC bytes to the application in the second step. So we can clearly write outside that char array, because for the length, it of course uses the size we specified in the packet header. No boundary checks except this 7FFC thingy. And yeah, by just using a larger value, we can write outside the, in this case, destination char array. However, obviously on the .data segment, we do not have return addresses. And this took me quite a while for the root cause analysis, because in case you want to put it in the stream now, I did a full or more or less full root cause analysis of this CVE, and we put it onto the company website or the company blog. So if you want to take a closer look at what exactly is broken and why it is exploitable the way it is, just read that blog post from me. But what it does is that eventually, we can take a look at that later, eventually you will hit a read-only page in the .data segment, and the string copy operation will continuously try to write to or onto those pages. Now, the first time, for some reason, or the first couple times, it is actually fine. It will not write onto the pages, but nothing special will happen. After the, I don't remember, like 20th time or so, it will call the CXX frame handler 3, which is like the structured exception handler thing on that Windows has, but C++ specific. And not C++, but CXX. If we take a look at this, we can just follow through it. Let me put that to the side. We can go to get PTD. As I said, for the root cause analysis, I just used the time travel debugging feature, which made this a lot easier to understand, because I just triggered the vulnerability, overrode the instruction pointer, or well, didn't override it, but hijacked it. And that actually nowadays gets to my head, like this overriding the instruction pointer thing. So many people say that. it gets a grip on me. But yeah, from there, I just stepped back in the time travel debugging feature of WinDBG until I actually understood what was going on. And we have this FLS get value function, which calls try get function. What it does is provide some static function arguments and returns the function pointer to the function we're trying to resolve. So basically, it's what is the function name? I think get proc address, where you supply or provide a function name and it returns the address, so you can just call it afterwards using that. This is basically the same thing. So it returns a function pointer. And if you take a look at the next basic block, we have a call to guard check icall function pointer. Now, IDA already gives it away. This time, it's guard check icall nop. What this does is kind of like the backwards compatibility thing, because if you have a application that is compiled with CFG, but the operating system does not support it, because both sides, the OS and the software, have to actively support and enable CFG in order to make use of it. So if the underlying OS does not support it, it will just go back to this guard check icall nop, which, if you take a look at it, where is it? Here, just returns. So as just like the nop instruction, it does nothing. And afterwards, we will call ESI. Now, ESI contains the function pointer that was returned back from this try get function. And since CFG is not active in this application, because somehow, I guess the developer decided we don't want to use ASLR and we don't want to use CFG, we can just call the address directly. Now, we can demonstrate that in WinDBG real quick. If we take this address and run the binary. Let me make this a bit bigger again. And apparently it's still in the buffer from earlier. So let's restart this. That is definitely not intended. Oh, and it's trying to download symbols, which is not going to work right now. Sims. Not as it should behave. I think it's registered as a post-mortem debugger, so let's just do it the other way of executing the binary and running the trigger file. Yeah, now, okay, timed out. Continue the execution. Okay, this looks better this time. Okay, so if we have a first chance exception, we continue from here. We end up at the add ESP, which is directly after the call to try-get function. And if we take a look at the return value, which is stored in EAX, we see that it's a bunch of 4-1s, so a bunch of A's. Now, if we step through the execution a bit, we will see that this is the call to the guard dispatch icall function pointer, which is just an op instruction. So if we step in here, we will simply return again. And afterwards, we have the call to ESI, which stores the function pointer that we overrode in the .data segment. Now, instead of just overriding it with A's, we can also stack pivot. And what I did was use a gadget to return back to the start of my buffer, where I placed a ROP chain in order to use virtual alloc to change the memory protection settings of a specific memory page where I stored my shellcode and just pop a calculator. So if we stop this and run the application again, we can also run Python poc.py. And this time, thanks to the demo gods, it actually worked. We got a calculator. The POC for that is not public yet. I don't know if I want to put it up there, but as I said, you can just take a look at the root cause analysis that we published on the Mentodea security blog, and building the ROP chain should not be too difficult. So we can see that if Ivanti, or as far as I know, they just bought this endpoint manager software from another company and then maintained it. If they actually enabled CFG, this would have been not exploitable, or maybe still, but way more difficult to actually exploit, because you need, in this case, you would need a ROP compatible, CFG compatible gadget to pivot the stack, instead of just one that does the trick. And we will come back later to that. I already ran ROPR yesterday, because usually I use RP++, also a well-known tool to extract ROP gadgets from a binary. And if I'm not mistaken, it's written in C or C++, and ROPR is written in Python. So yesterday evening, after being busy with the Flare on CTF for way too long already, I ran ROPR to showcase the difference between ROP gadgets and the CFG compatible ROP gadgets, which decreased the amount you can use by quite a lot. But yeah, we will take a look at that later. And I kept staring at my screen for way too long. So RP++ took like a second, 2 seconds to extract the gadgets. ROPR, it took 45 minutes. No, I did not finish Flare on yet. So yeah, we will not do that live. I already prepared that, because that would take way too long. But yeah, I have those files ready. We will take a look at them after the next CVE, which is 2019-0567. Connor McGarr has some great blog posts, I think 3 in total, about this CVE, where he walks you through the entire process of exploiting it, triggering the bug, exploiting it, bypassing various exploit mitigations like arbitrary code guard, CFG, DEP, ASLR, etc. The great thing about Chakra Core is that it's open source, so you can just pull the vulnerable version from GitHub and compile it both without and with CFG. So if we just take a look at the one without CFG, we can just execute the Chakra Core binary with the exploit.js. And what this does is it constructs a virtual function table, or it creates an object and then uses the arbitrary write primitive in order to corrupt that VF table. This is not the best way to do it because we could just overwrite a return address, but it highlights what CFG will do in the next step. So yeah, remember we constructed the fake virtual function table and just called the address within it in order to trigger the stack pivot, rob chain, and so on. Now, we also have the CFG version, and it is pretty much the same exploit. We just adjusted some offsets in order to accommodate for the changes that CFG introduces, because when you compile with CFG, a bit of code is injected. So all you have to do is just like change a few offsets. And we have the POC VF table. And this time, this is still from before, so ignore that. This time, it will not work. So we execute our rob chain, or at least it tells us that it does. But if we take a look at it in WinDBG, we can do file, and it's already ready. So just debug it and hit go. We see that we end up at anti-DLL RTL failfast2 with an int29 instruction, which is the CFG related one. And if we take a look right here, we see, well, security check failure or stack buffer overrun, and the subcode is 0xA, which is fast fail guard ICO check failure. So what happened here is that we used the VF table that we constructed ourselves, or like the object we constructed, and then hijacked the VF table. And CFG actually detected this. So we used the address of our stack pivoting gadget to move the control flow to our rob chain. And if you take a look at rob gadgets, the addresses, or like the gadgets themselves, what makes a rob gadget is the fact that it ends with a return instruction, or in the case of cop or job, with a call or jump instruction. And usually, especially for like rob gadgets, those are very close to the end of the function. And this means we are obviously not calling the address of a function itself, neither are we calling an address within the 16-byte boundary range. So CFG calls the validation function, this LDRP dispatch user call target, and this will just determine that the address of our stack pivoting gadget is invalid, and in the end call the RTL failfast2 function to just terminate the process in order to prevent us from actually exploiting it. So this is what CFG mitigates. And if we take a look, we also wrote a second POC. So we can execute Chakra Core with the POC return address. This time we are getting a calculator again. And as I mentioned before, CFG tries to protect the indirect function calls by validating the function, making it forward edge. It does not at all protect the return addresses on the stack. This is what, for example, CET does with the shadow stack, but CFG, if you are able to overwrite the return address and there is no CET, you're good to go. The next thing is also a misconception that a few people have. As soon as you actually got control over the instruction pointer, you're good to go as well. So in your rob chain, contrary to CET, just the very first gadget has to be CFG compatible. As soon as you got that gadget and somehow gained control over the instruction pointer and executed your first one, you don't have to worry about CFG again, because the control you have over the control flow is granular enough. So you can just circumvent CFG because just use the gadgets that, after the first gadget, the dispatch routine is not called anymore because there is no indirect function call again. As I said, contrary to CET, where I think, Stephen, you mentioned it while I was rebooting, you have to end with this specific instruction in order to return. So yeah, I mentioned that there were CFG compatible gadgets, and if we take a look at them, so I just used Dropper, which, as I said, took a very long time, like 45 or 50 minutes, and a lot of RAM as well, thanks to Python. We have this gadget txt with all the gadgets from the Chakra Core DLL. And you can see it's a massive text file. So you got a lot of gadgets you could use for stack pivoting and later on writing your upchain. And if we scroll down all to the end, we can see that we have like nearly 570,000 gadgets. And the chance that you have a working stack pivoting gadget you can use in there is very high. Now, if we take a look at the compatible gadgets and scroll all the way down, we have not even 2,000 gadgets that we can use for pivoting the stack.
These are the ones that are 16-byte aligned to the beginning of the function,
exactly,
right?
Exactly. Yeah. So theoretically, also the ones that are the function start. But yeah, so those are all the gadgets that are either valid start addresses of a function, but that's rather uncommon. Or, well, as you can see here, that one is probably one, or it's within the 16-byte boundary range. So CFG would say, okay, it is within the range of the edge case if the compiler did not align it because of whatever reason. So we allow the call as well. And we can see those gadgets you don't want to use. We have like a call instruction in here, so it would mess up a lot. And the chance that you find a working gadget for stack pivoting in here is rather low, or at least way lower than the full gadget list of like 570,000. As I said, you only have to find one compatible gadget in order to pivot the stack, then you're good to go, and you could go back to the all gadgets list. But bypassing CFG with compatible gadgets, in my opinion, is most of the time quite difficult or rather unlikely.
So you chose in that one to not use a stack pivot gadget, but to override a return pointer on the stack with the exploit, right?
Exactly. So what we did is just use the arbitrary read-write primitive to enumerate the stack, find a return address, and overwrite that one, because that's not covered by CFG at all and was definitely the easier way to go, at least for that CVE or that bug. So from my experience and my feeling, if you have the chance of bypassing CFG using something else than a CFG compatible ROP gadget, it's probably way easier.
Yeah, just a reminder for folks, the reason we want to stack pivot typically in heap exploits, whether it be like type confusion or use after free, is because the push, pop, and return instruction associated with the stack pointer, very powerful instructions. So if you pivot and exchange, typically the easiest way is just to do an exchange RAX, RSP, or whatever. And if RAX is pointing out at your virtual function table that you built, and you pivot that with a stack pointer, now you've got the stack pointer pointing at your virtual function table that you built, and you can leverage the returns and the push and the pops.
Exactly. So rather difficult, would not recommend. Microsoft actually had like a mitigation bounty program where you could report bypasses for CFG and get a bounty for that. However, all the techniques that are currently known were out of scope. And unfortunately, if you find a new bypass now, the bounty program does not exist anymore. So no money through that, unfortunately. But yeah, the other ways you could bypass or more circumvent CFG is just use a return address like we did for Chakra Core. Same as with like save SEH or ASLR, use an image that is not protected with CFG, because if you use an image that does not have CFG support, what the bitmap will basically be set to all ones. So every address within that image is determined a valid target address. Just like with save SEH on 32-bit, use an image that is not protected by it, so the entry will not get checked if it's actually a valid entry. There were some more exotic out of scope things that Microsoft put there, like instances of missing CFG instrumentation prior to an indirect function call due to compiler bugs or things like that. And bypasses that rely on CFG being coarse-grained. So this is kind of the other limitation. A, it's forward edge. It only protects indirect function calls. And B, it's coarse-grained. So that means it only checks if the address you want to call is valid according to the bitmap. It does not check, for example, if the type of function arguments you're providing or the number of function arguments you're providing is actually valid. So if the function expects one argument, but you provide two, CFG will not detect that and not protect you or your application from that. Same as exception handling, race conditions, and modifying read-only memory. In that case, you could just manipulate the bitmap itself. Those things were determined out of scope according to Microsoft. Yep.
Have you gone through the effort of actually identifying where the bitmap is stored and if there's any way to like visualize that?
So if we take a look at, should have it here somewhere, NTDLL. Somehow IDA does not want to open if I'm not upgrading the format.
Yeah, with IDA 9 now coming out, IDA Classroom and IDA 9 in general, the underlying API has changed, obviously, and all the plugins are broken. So like nothing works right now.
That's what I noticed as well, actually, for the Flare on reversing CTF. What I tried was binary or like patch diff specific shared object file. And due to the API update that Hexrace did with IDA 9, bindiff did not work at all. So had to go back to my IDA 8.3 in order to get that to work. So if we take a look at the LDRP dispatch user call target, IDA having some problems again. But yeah, basically to answer your question, what happens is during the compiling process, the linker will take like a list of all the valid functions. And there we go. Put them in a bitmap that is just stored in the image. So it's in a section that later on gets merged with read-only data. I do not remember the actual name of the data. It was RS something. I would have to look that up. But also during the compiling process, that section gets merged with read-only data. And if you take a look at the very first thing here, somehow IDA is very laggy right now. The very first instruction of the LDRP validate user call target just moves the address of the bitmap into the RDX register. So, oh yeah, here I actually have some comments. So what we have is move the base pointer of the bitmap into R11, and then it does a bit of like bitwise operation magic. It takes the target address from RAX, divides it by 512, and using this divided value, it calculates the address of the corresponding validation bit in the CFG bitmap. Using that bit, it then just makes some bitwise tests whether, depending on the bits set, it is determined a valid target address or not.
Yeah, nice,
But
cool. Yeah, I need to go read the Python code for Wropper and that extension, and probably explains it quite well too.
Yes, I was thinking of, if I find time after Flare-on, submit a pull request to RP++ to also implement this CFG filter there, because Wropper, in my opinion, it was just way too slow.
Yeah.
It took all 8 gigabytes of my virtual machine for 50 minutes. So yeah, but it did the trick, even though the gadgets were mostly not usable for pivoting the stack. And yeah, so for this function, I don't know if I want to go into like the bitwise operations. They are not that exciting in my opinion. All that is happening is using the target address. Microsoft did some very efficient calculations to, based on this address, calculate the offset into the bitmap, and then check the bit or the 2 bits at that address or at that offset to check, okay, is it valid or not? And depending on that, we either call the function or call LDRP dispatch user call target, which will in the end call this RTL failfast 2 with the subcode 0xa to kind of showcase or highlight that it was CFG related.
Yeah, cool. Yeah, and so like I was saying, when you dropped off at first, thankfully the demo gods came around and were generous after that. But that backwards edge validation, like you were talking about with the control flow enforcement, that's the one that's just going to be. I don't really see an easy way around that. It's very efficient. It's not much overhead, and just the fact that you've got to have that benign end branch 64 instruction there on every return is pretty brutal.
Yeah. To answer that question, the CFG call, yes, it should be in the input address table. So if you can somehow, Microsoft already mentioned that in the mitigation bounty program, if you can somehow manipulate memory, like, for example, the IAT or the CFG bitmap itself, which is in a read-only data segment, that is determined out of scope. Like, theoretically, yes. The problem is that with modifying this kind of read-only memory, you have to bypass the memory protection first to make it writable. And for that, like, I guess most of the time, if not all the time, you have to obtain some degree of code execution first, which, yeah, it's like an out of scope problem, because in my opinion, it can happen, but it's rather unlikely.
Yeah, and there's also import address table filtering if it's turned on via exploit gar, which goes and validates that the address that if you've overwritten the address in an imports table of where a function should be, it first goes and validates that it checks the library that function should reside in. And if the address that you're pointing to that you overwrote is not pointing to a range within that library's load address, then it terminates, and it caught you that way too. So it depends which mitigations are on.
Yeah. Which is, for all the talks I did on CFG and other exploit mitigations, my conclusion or result is what you have to do is take multiple exploit mitigations, stack protections, and so on, and just chain them together.
Yep.
Just like DAP and SLR was a pretty powerful combination because you required an info leak as well. If you combine CFG with Intel CET, that makes for a very powerful protection mechanism or combination.
Yep, absolutely. Cool. That's very informative. I think that's a super helpful presentation and demo to help folks understand what they're up against with Control Flow Guard. It is a mature mitigation at this point, and as I said at the beginning, Microsoft put a lot of faith in this mitigation to be enough to stop a large number of exploitation techniques, but it turns out that it's just not true. But then as you combine them with more and more modern mitigations, we're still in a position right now, though, as I also mentioned earlier, where most processors that are out there today don't support shadow stacks and control flow enforcement. So those are typically off. And at some point, Microsoft makes a decision and they say, we think enough systems out there are running a processor that can support it. So we'll either turn it on for everything and then maybe do a little check to see if the processor doesn't support it to turn it off. But it's a risk. Microsoft's in a tough position because if they turn the mitigations on and it breaks your applications, then you get upset at Microsoft. If they don't turn them on and your applications are vulnerable, then people get upset. So it's like a catch-22 that they're in, of course, a lot of times.
Exactly. Same problem with like the performance impact I mentioned. If the performance impact is too big, people will get mad at Microsoft. Why haven't you done a better job at implementing this? But yeah, you have to check what is more important. Perfect security would be nice, but if it comes at a performance impact that is too huge, it's just not realistic. And to answer another question I just spotted, this is anti-DLL for 64-bit. So R10 is just another register a CPU register that got introduced with 64-bit. So yeah, just another CPU register. And for XFG, I actually wanted to mention that as well. Microsoft developed XFG, which is the extended control flow guard, or CFG on steroids, how some people call it, which does additional checks, like it uses hashes on, I think, the function prototype or something like that to verify that it's valid. It was never actually shipped in like the graphical user interface of Visual Studio. You were able to compile with XFG using the command line compiler, but a couple months ago, Microsoft announced that it is deprecated or retired. So XFG, I don't know if it broke too much, but in the end, CFG, in my opinion, is good enough for what it is trying to mitigate. And yeah, XFG is not something we have to worry about from an attacker side, because you might find it in some applications that were compiled like a few months or years ago specifically with it, but it is not a thing anymore.
Cool. All right. Well, I think that takes us to the end here, unless you had something else you wanted to touch on. No?
Just real quick, because you mentioned it, kernel CFG is now a thing as well. It was not for some time because of the missing use of virtual-based security, because you could just override in the kernel, you could just override the bitmap. And now the bitmap for KCFG is in VTL1 space, so you cannot override it with kernel level permissions or access is not enough to override the bitmap in the kernel, because you need VTL1 permissions that got introduced with virtual-based security, or VBS. So yeah, since VBS got, I think it's on by default by now, at least on Windows 11, if I'm not mistaken, they decided that thanks to VBS, we can now also make use of CFG in the kernel.
Yeah, absolutely. Cool. Well, yeah, I think that takes us to the end. I wanted to put one thing up real quickly here. Can you see that on the screen now? Yep, it looks good. So
Yeah.
I mentioned this at the very beginning, but there weren't many folks on. If you're in the LA area, or if you can get to LA or Hollywood, same thing, on October 28th and 29th, we've got Hackfest Hollywood going on, and we've got a limited number of scholarship opportunities for a completely free entry, which was $425, but that gets waived. Just if you're interested, it's October 28th, 29th. It's 2 days, obviously, of talks. We've got an evening night out at Universal Studios, backstage, back lot, and a private tour for a fun thing to do afterward. But there's about 16 talks, multiple workshops on AI, offensive AI hacking, and other areas. We've got keynotes by David Weston at Microsoft, who's the head of OS security, and then also Yarden Shafir and many other speakers as well. But again, if you can get there, hit me up on Discord. I posted up the link a couple of times. I'll post it one more time, but reach out to me on Discord and DM. And if I still have any left, I will absolutely give you one. Just make sure that you're able to get there. All right. With that being said, next week, I should be having Laurie Wired on. I need to confirm with her, but that will be my guest next week. It'll be great to have her on. She's got an amazing channel and very talented. After that, we've got Jim Shoemaker coming on to talk about MFA bypass and do some demonstration using Evil Grade of like a MFA bypass on a custom, like not custom, but an application. It's pretty cool demo. I've seen it, and I think you'll like that one as well. And then we've also got Chompy coming up later in the month to talk about her process and methodology on bug hunting, and then some additional ones coming up in November. So everything's booked out for now. If you have any thoughts on who you'd like to see speak, please do go to the Discord channel and post that in the stream requests channel. And I'll post that up one more time right now. Discord.gg off by one security. So that's up there in the chat if you want to take a look. Otherwise, we will see you next week, and I'll send a tweet out as soon as I know whether or not I've got Laurie Wired confirmed or not, or what I'm going to do in place of that. So thanks, Snop. Again, really appreciate you coming out. That was an awesome demonstration and walkthrough. I think probably the best I've seen. So good job.
Thanks for having me.
For sure. All right. See you guys next time. Bye-bye.